In today's video, I would like to talk about shorts or short circuits. So when we measure a short circuit, normally we'd have a multimeter, put it into ohms range, and we would measure, in this example, is a piece of nickel, 0.1 ohms. This is another piece of nickel, 0.1 ohms, or a piece of solder. Not quite as easy, it's a bit longer, 0.3 ohms. Or I can demonstrate with a meter that has a slightly higher sensitivity and shorter leads. Zero point zero two, 0.05, and if I can get it, 0.22. So we can see that this meter, with a higher sensitivity, a higher resolution, slightly higher, is able to kind of determine the difference between those three items, but it's a very difficult measurement to make and not entirely clear. So to overcome the problem with regular multimeters and a 2-wire probe type measurement for very low resistances, we can get a device like this one. It's a milliohm meter, and these actually utilize a different kind of probe, which is a 4-terminal probe. It's called a Kelvin probe, and one set of probes is used to inject some current into the device under test. That current can be measured. The other set of probes is used to measure the voltage drop across the device, and then using Ohm's law it can calculate the resistance of the device being measured, so it can overcome any losses in the 2-probe setup. Now these devices are quite good, so I can just show you. I've got the 2 pieces of nickel here, so we'll measure the first one. So that's coming up as 4 milliohms. And 14 milliohms, 13 milliohms. And then my piece of solder here. So an 80 millimeter increment, which is that's 35, and it's 160 millimeters, 73, 110, etc. 4-wire Kelvin probe devices are great if you just want to measure a component or a piece of material. Absolutely no problem. You can make good contact with all 4 probes. Works great. The trouble is, if you're trying to diagnose a fault with a piece of equipment in a bus system or in a VRM or in any circuit that has multiple devices connected in parallel, where one of those devices may be faulty and the others not, or multiple devices faulty and one not faulty, or any combination really. So with that in mind, I've come up with 2 circuit ideas that I'm going to build and test I'd like to evaluate them for performance and cost and component count, and then select which one I believe is the best, and then go ahead and make a device that I can use a regular multimeter to try and measure difference between the three items that I've already shown, the two pieces of nickel and the piece of solder, using a regular multimeter. So this is the first circuit, pretty much stolen from the Texas Instruments datasheet. So this is using a TL431 as a reference to switch a transistor to create a constant current of approximately 50 milliamps. And then the second circuit, which is a much simpler circuit, uses an LM317 and a single resistor to create a constant current source of approximately 54 milliamps. Let's go over a couple of typical usage scenarios for this device. So we have here a schematic of a computer system. We can see here, for example, the system has a data bus and an address bus. Now, if in our example we find that there is a faulty memory chip or there's a short, so we could in our scenario be measuring across the data bus, and we may see a short circuit between, say, data line 0 and data line 1. But obviously they're on a bus, so the bus goes to multiple devices. So in our scenario, we could actually use this tester to localize the actual IC that's at fault by measuring each point on the data line that has a short to find the one with the lowest value, and then that would identify the component that was at fault. In another scenario, this is a multi-phase VRM, and we may find that, for example, in a power supply, there is a short circuit between the output voltage and ground, and it could be any of the phases that are causing the problem. It could be one of the high side or low side MOSFETs that are causing the problem. It could even be a shorted inductor. And using this device with single tip probes, it would be very easy to measure across each device itself to identify the one that had the lowest value, therefore identifying the actual short rather than a short on the whole system. And in the last scenario, it could be in a vehicle, in a car, a modern car with a bus system, CAN bus, for example. And in that system, various parts of the car connected together electrically on a bus, which would look something like this. It's traditionally it's a 2-wire bus system. Each module of the vehicle would have its own address. They're all connected in parallel with each other. Now again, in this scenario, one of these devices could be causing a short circuit on the bus itself, and with the 2-wire probe system you could use needle probes and actually pierce into the cables themselves at various points to determine which module was actually causing the short circuit on the bus. So here we have a mock-up of the first circuit. We have the transistor, which is a 2N2222, a TL431, a 2K2 resistor, and two 100 ohm resistors in parallel. You can go ahead and test this. So I'll bring in the meter. So let's just check the current first. So I've got 4.5 volts on my power supply, and we'll change this to current. Okay, so I've got 50.9 milliamps constant current source. Now, if we flip that millivolts, get some probes. So I've got my 2 pieces of nickel here. Start with those. So we'll start with the small bit. Okay, we're measuring 2.9 millivolts. And then on a slightly larger bit. Let's see. And I'll just do a couple of increments. So these are 80mm increments. Okay, we've got 2.16 millivolts. And then I'll come to the piece of solder. Okay, we've got 3.9, and then we'll go to 160mm by 2. There we go. 6.1. And if I can go to the next one, you can see it there. Okay, 7.94. Just quickly cobble together the LM317, 22 ohm resistor, couple of wires. Let's see the current that this thing is delivering. Okay, so we've got 55 milliamps. This piece of nickel. Got 2.52 millivolts. .54, and then on my piece of solder, .4, 6.6, and 8.8. Here are the results from the test that I've just done. The TL431/2N2222 combination produced the following results here and has a cost to me of around 77 pence. And the LM317 produced these results and has a cost of 65 pence. So on cost alone, it would appear that the LM317 would be the winner. And I believe also in the consistency of the results, the LM317 also appears to be the winner. The only thing that I did prefer about the TL431 circuit was it seemed to be a lot faster, but I'm going to go with the 317 based on its stability and cost. I've gathered the parts required. The total cost here is just under £3, consisting of a small project box to actually mount it in. We've got a battery box to hold 3 AAA batteries, a couple of terminals for the meter probes, a couple of 4mm plugs, the LM317, battery connector, resistor. I've added a potentiometer. I'll show you the revised circuit diagram in a moment, and a small piece of strip board. So here's the revised schematic diagram. I have added a single potentiometer here, and I've changed the value of this resistor. So the idea here is that I can actually adjust the output current, and a series resistor here to limit the maximum current. This is the meter that I intend to use. So I'm just going to measure the distances between the terminals here so I can transpose that onto my box to mount the 4mm plugs. So the pitch is 38mm. Yep, so it's 19 and 19. And the offset, the center, the common pin is actually offset a little bit from the other two. So let's just measure that. 3mm. Okay, I will transpose those measurements onto the box here, and I shall be back shortly. I've drilled the holes in the box. I'm going to just mount 3 cables onto my 4mm plugs here, so I'm going to go ahead and do that right now. Three. Okay. Now I'm going to screw these into the box. Wonky. Let's start that one again. Okay. Let's just soften that up. See that fits. Beautiful. Okay. I'm not sure if there's room to put these covers on inside. Yes, I think there is. That's good. Good. Okay. So the next thing I want to do is to mount the 2 sockets onto the side of the box. I'll just do those evenly spaced on the side. So I'll go ahead and drill the holes, and I'll be back when I've done that. So you can go ahead and mount the connectors. Good. So next I just want to get a gauge of how much space I've got left for my circuit board. So I'm just going to mark that very roughly. I'm just going to go and cut this to size. I shall be back in a moment. Board cut. So now fits in there. I know how much PCB I've got to play with. So I think next I'll go ahead and actually build the circuit onto the piece of Vero board. So we'll get set up for that, and I shall be back. Because I'm going to mount an adjustment pot on this guy now, which I think I'm going to have to put a hole in the top of the box to make that adjustment. It really means I'm going to have to mount the LM317 on the bottom of the board. I think it's not the easiest thing to achieve, but I think it's going to be kind of necessary. So with that in mind, I'm going to try and solder that on the wrong way around. Focus that a little bit better. And just get it soldered, and then we'll just come back and clean that up. Doesn't look too bad. I'll put a piece of Kapton tape on there before I'm finished to stop any shorts, but for now we'll just carry on. Okay, so next we have 10 ohm resistor. So the 10 ohm resistor is going to go to pin 2. I've got a Vero board cutter here. These are really great. I don't even know if you can still buy these. I've had this for years. Very useful. So it just enables us to cut the tracks. Okay. Then we've got the potentiometer, which is going to go between pins 1 and 2. Now, I do know from previous experience that these legs on these potentiometers do not actually fit through the holes in the Vero board. So I'm just going to go and find a small drill bit just to open these holes up a little bit, just so that will fit. I've got a 1.1mm drill mounted into a small pin chuck here. So now we just need to mark the holes that I need to enlarge, which will be Okay, we can go ahead and mount the potentiometer. Okay, so now we just need power in and power out. So I'm just going to go ahead and mount a couple of these small battery terminals onto here, and then I can use connectors. I think that's probably the best thing to do. So we'll just pop a couple of these on here. So basically we've got one which is making contact with pin 1 and one is making contact with pin 3. Let's go ahead and solder those. Just need to cut the track that's going from the potentiometer. It's not very straight, let's just straighten that out. Okay, I think that should be good enough. Okay, we just need to cut the track, which will be that track there. I'm just going to go ahead and mark this so there's no confusion for in and out. Add some Kapton tape. Should work. As is usual, I've made a mistake, so I put this on the wrong side because I need to mount this in the lid. So a bit of reverse engineering is required. I'll go ahead and do that. Well, doesn't mean I don't have to put the tape on because I've now got a natural barrier, which is okay, I guess. I've just gone ahead and popped out the unused wires out of those two connectors because we only need power in and power out on this guy. It's one of the beauties of this circuit is it doesn't actually consume any power when it's not being used, because effectively it's just in series with the supply. So at this point I just want to go ahead and make sure this is actually working. So I've got my bench power supply here on 4.5 volts. So that is supply side. Need ground to the meter, to milliamps, and that into that. It's promising. Okay, 16 milliamps. So if I go ahead and adjust this, so you guys can see. can go from 120 milliamps down to 11 milliamps. Perfect. So the next thing I need to do is to try and mount this onto the lid. I'm not really sure how I'm going to achieve that at the moment, but before I do any of that, I actually need to make a hole for the adjustment pot. So I'll just go ahead and I'll measure something up and drill a hole in this. So I ended up using a few of these hex spacers and screwing it to the cover. It's not the best job. This is a prototype though, so I think that's okay. Right, so next I'm just going to go ahead and connect everything up, and then we can give it a test. So I'm just going to do that. While I think about it, what I have actually decided to do is to put a push button switch in here also. I think I will mount that in that space there, and then that's going to enable me to just press a button to actually set the current limit. I think was a good idea. So I'm going to go ahead and drill another hole in the cover, mount this switch. Right, the switch is mounted. I think the last thing that I need to do before I make all the connections is to put a hole inside so I can get the power into the unit. So I'm going to go ahead, drill a small hole in the side. I'm just going to have a fly lead hanging out for the power. So back in a moment. Hole drilled. So now I just need to go and make all of the connections. And I can do that. So the output is pin 1, which is this one. So I should just be able to unplug that actually. Just try a little bit off of that. I'm not worried about making it overly neat because this is a prototype. Make it functional. So that goes to power. Then it's just a matter of connecting the switch. Makes sense to make that. Put bits of heat shrink on there. Switch. Very difficult doing this on camera. Anyway, okay, so let's get the power cable in. Now basically we need to join those two together. Okay, needs enough. Right, we can join these two together. heat shrink for those. And heat shrink. Right, I think I'm ready to test. Won't clip it together yet. So here's the meter. So that should plug into there. And let's put it on to milliamps range. Need some power. Okay, just give me a second. I need to figure out some power. I found another one of these 3 connectors. Okay, bench power to start with. So hopefully if I press the button, yep, we can see our current. Let's set that for 50 milliamps. Milliamps. Okie dokie. I'm just going to rearrange this because my bench power supply is actually on the left side, which is causing everything to be a little bit upside down. So I'm just going to have a bit of a rearrange. So I actually went ahead and connected the battery box that I intend to use for this guy anyway. So I just did that while you weren't watching. It does have an on-off switch, although, as I've said, this circuit doesn't actually consume any power when it's not in operation, which is one of the great things about it. But anyway, so I have the battery box connected. We're still in current range. Press the button. So we've got 52 milliamps. Now, if I go and get some test probes. Oh, they're tight. Just in the center. Why? Chinese rubbish. Right, I've managed to get the test lead in. So put this onto millivolts range. Find the nickel strip, which is here. So the larger piece, we have 4.2 millivolts. The smaller piece, we have 5.2 millivolts. Now that I know that it actually works, I'm just going to clip it together, tidy everything up a little bit, and then we can do a bit more testing. So here's the finished prototype. And as I say, it is just a prototype. It's kind of experimental. But there's the unit. So we've got 2 jacks at the front for the test probes, 3 pins at the bottom that go into the meter, the button on the top to enable setup mode, if you like, and then power coming out the left. So we should just be able to clip that into the meter, connect a couple of probes, connect the power, so to start with, we can set the test current. So currently it's at 20 milliamps. So it goes from 11 to 120. So let's just set that for, let's go with 60. Okay. Now I can come along and test one of my strips. Oh, need to go to millivolts. Okay, so we have 4.6 millivolts on that one. 3.6 on that. And if I come back to my piece of solder that I did earlier with the incremented solder, 160 millimeters, 8. Bearing in mind that I've got the current set to 60 milliamps at the moment. Then we've got 10, and 13. Let me set the test current down a little. Let's go 20 milliamps. Then on the smaller piece of copper, we've got 1.5 millivolts. The larger piece, 1.1. Again, we've got 1.7, 3.4. That seems to max out. 2.6, 3.7, and 4.7. And lastly, we'll set a much higher test current, 115 milliamps. 24. 12. 6.4. 12. 15. And then from there to there, 13. And if I go really short distances, so this is about 1.5 centimeters. .6, and then we go down to about 5 millimeters. We've got 5.3, 5.2. Okay, guys, well, I think as a prototype, it works reasonably well. Does really need to have some further testing, but on the whole, I think it's quite good. Now, I am considering giving this away to a lucky UK-based subscriber. So if you would be interested in receiving this totally free of charge, then please leave a comment and I will hold some kind of competition, but it will have to be for UK only subscribers, I'm afraid. And I hope you enjoyed that.